Okay, in this video we are going to look at exponential functions. So we're introducing a new function to add to our library or our list of functions. And exponential functions look like this. F of x is equal to c times a to the x. So c is a constant, it's a real number. A is a constant, it's a real number. And now x is our variable and it's up in the exponent. So these are pretty easy to identify because your variable is going to be in the exponent, which is why it's called exponential functions. All right, so what does this stuff over here mean? Is it important? Does it matter? Well, a little bit, yes. So a has to be positive. So a is the base of our exponential function right here. A can't be 0 because if it was 0, 0 to the x would just be 0, and this wouldn't be an exponential function anymore. So it's not really that it doesn't exist, just that it wouldn't be exponential. What happens when a is negative? Well, if a was negative, then x couldn't be anything that we want it to be. We want x to exist everywhere. And for things that are fractions, like 1/2, that's the same as a square root. And remember, when you have a negative to the square root, that doesn't exist. So what happens is if a is negative, this doesn't exist everywhere, we kind of end up with a mess, and it's not going to be a function. It's definitely not going to be a smooth, continuous function like we want it to be. So in order for this to work the way that we want it to, a's got to be positive, okay? So that part is pretty important. Our base has to be positive. Now c can't be 0, because if this was 0, the whole thing would be 0. Again, not exponential anymore. And a can't be 1, because 1 to the anything is just 1. And it's not exponential anymore. So these two aren't that big of a deal. It's not like the function's not going to exist. It's just they wouldn't be exponential if that was true. Okay, so the base is positive. That's going to be kind of a big deal. So we're going to be looking at things that look like 2 to the x, or 3 to the x, or maybe 1/2 to the x, things like this. We have a whole number, or a fraction, raised to an exponent. That's a variable. Most of the things that we look at, the c out front is going to be a 1, just to keep things a little bit simpler. But if we did have something like 5 times 2 to the x, remember your exponential rules, these cannot be combined. They either have to have the same base or the same exponent, and these do not. So there's no simpler way to write something like this. It has to stay in that form, which is why our exponential function is written this way. Okay, so since this is a new function to us, we need to know what's going on. And a lot of times when we do that, we want to look at the graph and we want to plug in some values to see what's happening and see if we can find a pattern. So let's go ahead and look at 2 to the x. Okay, that's one of our simpler functions just because the numbers stay smaller. And let's see what the graph looks like. So let me put a graph in here. That's way better than I can draw. And let's look at some values for this. So we're going to plug in some x and y values and see if we can figure out what's going on. Alright, now, like I said, you can plug in anything for x because the base is positive, so we're good. So let's see what happens when we plug in some positives and some negatives. Okay, so we're just going to pick some values for x. We're going to pick more values than you normally would, but we don't know what it looks like yet, so we're going to see what's happening. So we're going to plug in -3. We've got 2 to the -3. And remember from our review video, if you have a negative exponent, that means reciprocal. So this is the same as 1 over 2 to the third. 2 to the third is 2 times 2 times 2 is 8. So this is the same as 1/8. Okay, we looked at these in that review video. If you haven't seen that, you might want to go back and look. All right, 2 to the -2. That's the same as 1 over 2 squared. Whoops, that looks like a 3, sorry. 2 squared. And that's going to be 1 over 4. 2 to the -1 is 1 over 2 to the 1, or just 2, so 1/2. 2 to the 0, remember anything to the 0 is 1. 2 to the 1 is just 2. 2 squared is 2 times 2 is 4, and 2 to the third is 2 times 2 times 2 is 8. Okay, so now we've got some values for 2 to the x. Let's see if we can figure out what's going on. So looking at the left side first, let's start from 0 and work our way to the left. So at 0 we have 1. And then at -1 we have 1/2. At -2 we have 1/4. At -3 we have 1/8. Okay, if we had extended our table out, at -4 we'd have 1/16. then 132, then 1 over 64, 1 over 128. So these numbers are going to keep getting smaller and smaller and smaller. They're going to keep getting chopped in half. They're going to get closer and closer to 0, but we can never actually reach 0. We're just going to keep cutting it in half. So remember, if we get closer and closer to 0 without actually reaching it, then that's going to become an asymptote. So it's kind of hard for me to draw really, really close without touching it. But it's going to look something like that with this now being an asymptote. Okay, so on the left-hand side, we're going to get closer and closer to that asymptote. All right, on the right-hand side, starting from 0, 1, we've already got that plotted. At 1, we get 2. At 2, we get 4. At 1, we get 2. 2, we get 4. At 3, we get 8. 4, 6, 8. If we could continue this on, we'd get 416, 532, 664, and so on. So we get 16, 32, 64, 128. These numbers would keep getting bigger, and they get bigger very quickly. So on the right-hand side, we look something like this. Okay? So this is the shape of an exponential function. They will all look very similar to this. They kind of have this ski slope shape to them, okay, or backwards L, rounded backwards L. They're all very similar to this. Okay, so 2 to the x is kind of our base example for that. So let's also look at 3 to the x and see how it compares. We also looked at the numbers for 3 to the x in that that review video. So I'm going to go through these a little bit faster. All right, so -3, -2, -1, 0, 1, 2, 3. So when we plug these in, 3 to the -3, that's reciprocal, and 3 to the third is 27. 3 to the -2, that's reciprocal, and 3 squared is 9. 3 to the -1, that's reciprocal, and we just get 1/3. 3 to the 0, anything to the 0 is 1. 3 to the 1 is 3. 3 squared is 9. And 3 to the third, 3 times 3 times 3 is 27. Okay, so again, we get this chart that we saw before. You see 3, 9, 27, 1/3, 1/9, 1/27. We could keep going from there, but we're not going to be able to graph all this as it is. Okay, so again, starting at 0 and going to the left. At 0, we have 1, and you'll notice that that overlaps our 2 to the x graph. And that's because anything to the 0 is equal to 1. So it's not going to matter what your base is. At 0, you're going to have this point of 1. Let me draw in that this one is 2 to the x. Okay, so, which color am I on? One color. Okay, going to the left. So we're going to have 1/3, 1/9, and 1/27. So 1/3 is going to be a little bit below that. 1/9, I'm not really going to be able to draw these because they're getting so tiny. 1/27, if we kept going, it would be 1 over 81, and so on. So these are going to get very small very fast. So this is actually going to be under our other graph. Okay, so our blue graph is underneath our red graph. All right, going to the right, starting at 0, 1, then at 1 we have 3, at 2 we have 9, and at 3 we have 27. We're already way off the chart, and then 81, and so on. So on the right-hand side, we get bigger faster. And so it looks like this. Okay, so based on this, can we predict what 4 to the x might look like? What does 4 to the x look like? Well, we can see when we did 3 to the x, when it's on the negative side, the numbers get smaller faster, and on the positive side, they get bigger faster. So the same pattern should continue with 4 to the x. The smaller numbers get smaller. Let's see if I can cram this in here. The bigger numbers get bigger, and 4 to the x is going to look something like that. Okay, you can also graph these on your graphing calculator if you like, and you can kind of see the comparison there, and you can zoom in if you want to see what's going on around here. But again, they all cross at 0, 1, and we kind of have that L shape. The higher the base, the more of an L shape it is. The lower the base, the more rounded it is, kind of like a ski slope. All right, so this is our basic graph for exponential functions. Now, one thing that I want to introduce here, and we'll talk about it more in class, is base E. So E is sometimes called Euler's number or the natural constant, and E is equal to about the same as 2.72. Okay, so where does this come from? Well, if you remember from way back in math, you should have learned about pi. And pi kept coming up in geometry. So the Greeks were working with geometry. This number kept coming up over and over and over again. They finally they're like, fine, okay, this is going to come up all the time. We're going to give it a name. We're going to call it pi. And for them, they gave it a letter. Pi was one of their letters, and so that we still call that pi. Pi is 3.14. Well, when you're doing these problems with exponential functions and real-life models, a number that keeps coming up over and over and over again is 2.72. Just like pi, it comes out of natural applications, and just like pi, it is a non-terminating, non-repeating decimal. So I should actually have approximately for both of these. Okay, so when you see E, think of it as being similar to pi, and it's between 2 and 3. So if I wanted to graph this, if I want to graph y is equal to e to the x, how would I graph that? Well, it's between 2 and 3. It's a little bit closer to 3 than it is 2. So basically the graph's going to look a lot like 3 to the x. Okay, and rather than going in and punching in numbers for this, which we would need a calculator for, we can just say, well, e to the x is very similar to 3 to the x. It's just a little bit smaller. So it's going to be like maybe right here between 2 and 3, a little bit closer to 3. And then, I don't know if I can even draw it in here. It's going to be between them like that. Okay, so e to the x you can think of as being very, very similar in value to 3 to the x. And it's a value that comes up very often, so we use it a lot in these applications. All right, you can also put this into your graphing calculator. Any of these you can put in your graphing calculator. So if you needed actual values for it, it's probably easier in the graphing calculator because it's a decimal and you'd have to be punching in decimals over and over again. All right, so we're going to look at more of these graphs in class. This kind of gives us a foundation for what they're going to look like and how the exponential functions work.